Hello everyone, welcome back to Xenon Circuits. This will be the third lecture in the crash course on Basic Electronics series. This is the typical question asked in most of the core electronic based companies in their campus placement drive. We will solve this problem in a step-by-step approach. First, we'll try to understand the question. The question is find RAB at DC steady state condition. So we need to find the equivalent resistance across the nodes A and B at DC steady state condition. So this is the biggest hint for us, right? So the hint is DC steady state, right? And what are all the elements we have here? We have a resistor, we have an inductor, we have a capacitor, and we have an ammeter. Okay. Now we need to understand what is DC steady state condition. First of all, we should know what is DC. DC is direct current, and in DC there are two states, which is steady state, transient, and steady state. Okay. So what is transient and what is steady state? Maybe before understanding these two, we should try to plot how DC signals usually would appear. Okay. So let me just redraw this again. The quantities, sorry, the quantity in X axis would be time, and the quantity in Y axis would be either voltage or current, and how they usually appear is like this. Okay, so assume that this is a straight line. Okay, and from the origin till this rise point of either VDC or IDC is known as the transient state. Okay, and the constant duration after the transient state is known as steady state. Transient state doesn't necessarily mean the rise time. In some cases, right, it can be of this sort as well, where it will be falling suddenly and then will be reaching a constant value. So it can be either it rises suddenly and reaches a constant value, or it falls suddenly from a peak value and then reaches a constant value. So transient duration can be either this rise or fall. Okay, and then post that transient duration, it would be constant, the quantity, whether it's voltage or current. Okay, so now we got to know what is steady state and transient, and now we should try to understand how the resistors, inductors, capacitors, and ammeter is going to behave in the steady state, because that's what we need now, right? And you are aware that the voltage and current relation in a resistor is directly proportional, right? As per Ohm's law, at constant temperature, voltage is directly proportional to current, and the proportionality constant is resistance. Okay. Now, let's take a look at inductor. So, for an inductor, how the voltage and current are related is the voltage across an inductor is directly proportional to the rate of change of current through it. Okay, and the proportionality constant here is inductance. And similarly, for a capacitor, charge stored across a capacitor is directly proportional to the voltage applied across it, and the proportionality constant is capacitance. If we differentiate on both the sides, this becomes dq by dt, that is equal to c dv by dt. dq by dt is nothing but the rate of change of charge, which is nothing but current, right? So I is equal to c dv by dt. So this is the relationship between current and voltage across the capacitor. Okay, now we'll take a look at the ammeter. First of all, the basic of ammeter everyone should be aware, right? So what is the role of an ammeter? Ammeter is used to measure current in a particular node, right? Or in a particular branch. So let's say there is a source, voltage source, across which a resistor is connected. Okay, and if we want to measure the current that is drawn by this resistor, what we have to do? We have to connect an ammeter, right? So how do we connect that? So we have the supply, and then we have the resistor, and then we connect an ammeter. Okay, why we doing this by connecting it in series? The reason is, if you want to measure current in a particular node or a branch, we have to connect the ammeter in series across which element has to be measured. Okay, in case if we connect the ammeter across the resistor parallelly, what will happen? The current will get divided ideally, right? But, and we do know that ammeter has an internal resistance of 0. Okay, so what happens if the ammeter is connected in parallel? We know that the internal resistance of an ideal ammeter is 0, right? Which means it is a short circuit, correct? So if we just replace the ideal ammeter with its equivalent resistor model, what is going to happen? The current that is about to enter across R will be entering through this ammeter, right? There won't be any current entering through this resistor. This is just a simple element, right? If let's say imagine we have a network of several elements, then it is very tedious, or I mean the circuit functionality won't be happening, correct? So the best way to connect an ammeter is connecting it in series across the element through which the current has to be measured in order to capture the current values, right? Okay, only this would be equivalent to this, the existing circuit, so that the circuit functionality also doesn't change, and we will be also able to read the current. Okay, so now we got to know the working of ammeter, inductor, capacitor, right? Now let's equate this learnings into the question what was asked earlier. So at DC steady state condition, how does an inductor, capacitor and ammeter is going to behave? we know that the resistor is going to behave the same, there won't be any change. Now for an inductor and capacitor, we can see that we have either the current or the voltage as changing with respect to time, and we know that at steady state condition the change of the quantity with respect to time, whether it is current or voltage, is going to be zero, right? From this curve we can understand that. Okay, so what happens, the voltage across the inductor will become zero if we apply this di by dt as zero at steady state condition, and then similarly the current through the capacitor is going to become zero. Okay, and as the voltage is zero, we can safely assume that the inductor becomes short circuited, because if voltage is zero, then the resistance is also zero, right? And as the current through the capacitor becomes zero at steady state condition, we can safely assume that the capacitor can be modeled as an open circuit. Okay, inductor as short circuit. Now what happens to the ammeter? So the ammeter ideally has an internal resistance of 0, or it is a short circuit. Now at steady state condition, it doesn't matter, right? It is just an instrument to measure the current. Okay, so whether we have an AC or a DC current, the ammeter's functionality is not going to vary, because it is just a single wire with zero resistance or infinitely low resistance in terms of a practical ammeter, right? Now let's go to the circuit again and redraw it at our end. Okay, let me just copy this for my reference. Okay, let's start simplifying this circuit. So that is the node A connected to resistor 2 ohm. The resistor will remain same as we know, and then the inductor becomes a short circuit. Then we have a resistor 2 ohm, and then below that we have a resistor of 4 ohm, and then we have a capacitor, so it becomes open circuit. Now we have the node B. From node B we have 5 ohms, which remains the same, and then we have 3 ohms, and then we have a ammeter, which becomes a short circuit, right? So now if we are going to send an electron here, the electron will prefer to travel in which path? Either through the 2 ohms path or the short circuit path. So it would prefer to travel in this path, right? And then once it enters here, then it sees 3 paths from these nodes are shorted, right? 1, 2 and 3. If we give the name, what is going to happen? So let's say this is A, this is also A, correct? This is also A and this is also A. And as this is getting shorted, this becomes A, this becomes A, this becomes A, right? So just by giving the node names, we can find that the resistance across A and B is going to be 5 ohm, right? But we'll just prove that. Okay, so what is going to happen? Now that we have a short here, this element becomes redundant. Okay, and now that we have an open here, so these two elements are just floating, correct, and not connected to any other nodes. Okay, then This 3 ohm is connected across the nodes A alone, right? So this also becomes redundant. Okay, so our AB is nothing but 5 ohms. I hope you understood the concept of steady state and how inductor, capacitor, resistors and ammeters are behaving in these conditions. Let's learn about some new concepts in the next video. Thank you so much.